Okay, we are going to talk about section 1.6, preview to inverse functions. So we get a taste of what an inverse function is here. And I want to start with an analogy of a box, a gift box, and you're wrapping this present. And when you wrap a present, you take the object and you put a bunch of wrapping paper around it and then some tape, you tape it all up, and then maybe you put a ribbon on it, and then you put a bow on it. And so you've gone through this process. You had this object, you wrapped it up. So the inverse process is we're going to undo all of that, and we kind of go in reverse order. We'll take the bow off, and then we'll take the ribbon off, and then we'll take all the tape off, and then we'll take the wrapping paper off. And so this is the idea of an inverse function, that there's a process that happens, and then there's a process that undoes what happens. So we have f of x is going to take x to y, and then the inverse function, which the notation for that looks like f with a little -1. It's not an exponent, it's just a name of the function, takes that output y and sends it back to its original input x. So this inverse function, f of -1, is going to take those outputs of f and send them back to their original inputs. So where our original function was an assigner, now we're going to have an inverse function that takes things back to their originals, takes outputs of f back to their original inputs. And sometimes you can do this and sometimes you can't. And we're going to look at a number of examples. So some functions can be reversed and some cannot. And we're going to get good at being able to tell when they can and when they can't. You know, one function that we want to think about is one we've seen before. It's where people got assigned their ages in a family. So Ryan, the function was going to assign Ryan to 42, Jessica to 41, Tyler and Maria to 11, and Kevin to 6. And we think, well, what would the inverse relationship look like? It would take the numbers back to the names of the people. So 42 would go back to Ryan, and 41, so 42 goes back to Ryan, 41 would go back to Jessica, and then 11, we would want to send that back to Tyler. So this is a problem because 11 should go back to Tyler, but it also needs to go back to Maria because she's 11. So this inverse function, inverse relationship, wants to send one input, 11, back to two outputs. So can 11 get assigned to two different outputs? In a function, no. So this right here is a problem, and this indicates that f inverse actually doesn't exist. So this function has no inverse function because 11, which was an original output of f of x, you know, where would we send it back to? There's two places that it wants to go back to. So this is an example of a function that cannot be reversed. The next example we're going to look at is about car speed and the braking distance. And so think about maybe you're an investigator at a scene of an accident and you can't tell how fast the car was going that caused the accident, but you can read off skid marks. They're still sitting there. And so you have an idea of what the braking distance of this vehicle was. So our two tools that we're going to use as the investigator in this scene of the accident are, we can measure the skid marks that are there, and luckily we also have a model that gives braking distance as a function of speed. So this is a model that was probably, you know, constructed from lots of data over time, but this model tells us at a certain speed what the braking distance should be. And we're going to use these two pieces of information to try to determine whether a car was speeding or not. So here's the function d equals f of s, and so our inputs are s and our outputs are d distance. It's a function that gives braking distance in feet as a function of speed in miles per hour. And so d is the output, so d is, this equal sign means is, and d is a function of, that's what the f is saying, a function of speed. And speed is our input. And it equals this big honkin' long formula. So you give me a speed, I can give you a braking distance, is what this formula, this function, tells us. And we can take it back. So what we want to know is if we knew a certain braking distance, could we unravel this and tell what the speed of the car was? So for example, if I see skid marks that are 107 feet, could I go back and determine what the speed of the car was? And this is sort of inverting the original function. Can we determine what the speed of the car was? Okay, so I went ahead and input that function into Desmos, and I used x and y's just because Desmos sort of prefers that, but I know this is my input value, the x, and this is my output value. So the x is representing the s in the function, and the y is representing the d in the function. And this is what I get when I first graph it. I know that I'm going to have to change the values of my x-axis and y-axis because, frankly, you know, knowing let's see, this is my input axis, so knowing 10 miles per hour and 10 feet in braking distance isn't going to be enough, so I need to kind of open this up. And I'll go to settings and I'll think, you know, what do I need for a potential horizontal axis? So this is my speed, so I'm going to take it all the way up to like 100 and I don't know, 40 miles per hour. And then my y-axis, the braking distance, I really don't know either, but so I'll experiment. Is 2,000 going to be enough? And it looks like it is. So this kind of here gives me a good picture of what the function's doing at different speeds. So again, the horizontal axis is speed. So at 100 miles per hour, I can see kind of the braking distance. I probably don't need all the way up to 2,000, so maybe I'll take it down to let's see, like a y value of maybe just 1,500 is more accurate. Okay, so this is the graph that I'm going to try to sort of tease out some information about the inverse function from. So here along the horizontal axis, I have the speed of the car, s, which is my input value for the function, always on the horizontal axis. And then on the vertical axis here, I have my output for this function, which is d, the braking distance. And so each of these numbers along my vertical axis are representing a braking distance. Okay, so what we're interested in is we see that the skid marks are 107 feet. So we have to think, are 107 feet, is that an input or an output value? Okay, that's not a speed, it's a distance. So it is a braking distance, which means it's an output value. So knowing this, could we determine speed? So knowing an output value, could we determine the input value? And so our strategy is going to be, okay, well, let's find out where that output value of 107 was. It's probably about right here somewhere. And from that, could we use the function to determine what the input value was for that output? So back on Desmos, I know that my output is 107. So my output is 107. Whoops. The only question is, should I let x or y equal that? And output is y in Desmos. So I'm going to say, what happens when y equals 107? Okay, so this is really informative. If my output is 107, this blue horizontal line is 107, then my input is 50.484. So that's something I can use. So in this example, we're able to take an output and use the graph of the function to determine what the input must have been. So sort of reversing the process of a function and in essence thinking of what the inverse of this function would have been. So if the distance, the braking distance was 107 feet, graphically we were able to determine that the speed must have been 50.484 miles per hour, and maybe that was speeding, maybe it wasn't. You know, maybe you're in a residential area where the speed limit's 25, so that would have definitely contributed to the accident. So I want to talk about some notation. With this information, we can say F inverse of 107 equals 50.484. So this little 1 above your function name is not an exponent. It is telling you that you're talking about, this is the notation for the inverse function of the function f. So f inverse of 107, this was our input. The inputs of the inverse function are the outputs of the original. Okay, so this little -1 is not an exponent, it's read f inverse. It indicates the inverse function. This 107 was an output for f and is an input of f inverse. This 50.484, this is an input of f, it's a speed, and it is an output of f inverse. This is how it always goes with a function and its inverse. The input of the inverse function are the outputs of the original function, and the outputs of the inverse function are the inputs of the original function. I know that's a lot of words. We're going to look at more examples, but first let's look at the definition of the formal definition of inverse function. So a function f inverse, read f inverse, is the function whose inputs are the outputs of f and whose outputs are the inputs of f. Let's first of all, let's close that, and then let's take a look at our function machine and what another way of thinking about this. So we've talked before about how a function takes this input x and it goes into the function, and f assigns it to some output y. And so now we have some inverse function, f inverse, where into this function we're putting our old outputs of f, and after it goes through the process of this inverse function, that output gets assigned back to its input. Let's look at another example. In this example, we have that the length in inches of Julie's hair t days after a haircut is this function here. Okay, so if you tell me a certain number of days, like 5 days after her haircut, then I can tell you what the length of Julie's hair is. So my input is time and my output is this length of hair. And the first thing we're asked to determine is, for the function f, the original function, what is the independent variable and what is the dependent variable? So the independent variable, let's see, that's our input. So for our original function f, our input is days. So t, or number of days, and then our dependent variable of the function f is the output, which is length of hair. So these are things we could have answered, you know, a week ago. For a function, we can pretty easily tell what the independent and the dependent variable is. Now the next question is going to be about the inverse function. So now we're asked to find the independent variable and the dependent variable of the inverse function. So think about what this inverse function would do. Here's the original function. The inverse function would say, okay, if I know the length of her hair, then I should be able to tell you the days, the time. So if I know the length, that would be my input, then I should be able to tell you the time, or the number of days. So for my inverse function, the independent variable will be length of hair. This was the output for the original function, and my dependent variable will be t. Then the question can be asked, is f inverse really a function? And what do I mean by that? Well, think back to the first example where we had names and ages of people, and we weren't able to send back the ages because 11 years old would have gone to 2 different people. So the inverse relationship was not a function. So do we run into any problems like that in this situation? In other words, think about the inverse function. When we have a length of hair and we want to send it back to the day that it came from, is there any way that this length here, might get sent to 2 different days? Well, hair usually grows pretty consistently. I mean, it's like microscopically, but from one day to the next, you would expect a continual growth just because of how bodies work. And so, you know, if we measure very finely, we can tell from one day to the next that growth has occurred. And so there's never going to be 2 days where the length of the hair is actually the same. And so we could say, no, I mean, yes, it's fine for this inverse relationship to be a function, because knowing the length of hair, we would be able to map it to exactly, you know, 1 day. So no 2 days are going to share the same length of hair, we'll say. And so this inverse relationship really is a function. So we believe this is a function because we're going to assume hair is always growing. No length, which is the input for the inverse, would have to be assigned to 2 different days. You might think of it this way, that you give me a length and the inverse function will give me what day that length happened on. So a length will not share 2 days, we're assuming. And so yeah, it is a function. Let's look at an example of a situation that turns out the inverse function is not a function. So here's our next example, students and the number of hours worked last week. So this is typical of an example in the textbook. Sometimes the words can be kind of terse, but we have to figure out which is the input and which is the output. Students and the number of hours worked last week. In this phrasing, we're going to take students to be the input and number of hours worked last week to be the output. So we could write it like this. Our function f takes a student and assigns it to the number of hours worked. This is how we'll think of our function. So here again, our first question is for the function f, identify the independent variable and the dependent variable. Well, we decided that the independent variable was the student and the dependent variable was the number of hours they worked. So the very next question I'm going to ask is, does this function have an inverse function? So when this is the only information we have to think about, is it possible to reverse this process? So say that you have two different, you have maybe 5 students and we're assigning them the number of hours they worked. Well, what if Joe and Mary both work 30 hours? We have to assume that that's possible in this scenario. And in that case, we couldn't map 30 back to just one output. And so it looks just from this information that it's not possible to reverse this process because it's very likely that 2 of the original inputs will have the same output and we couldn't reverse that. So we're going to say, well, I'm going to say no, it doesn't have an inverse because of the possibility that 2 inputs from the original function are sharing an output. So to answer this question, does f have an inverse function? We decided, for example, 30 hours could have to be assigned back to multiple students, and that's not legal in a function. So we're going to say no, based just off of this sketchy information that we have, meaning we don't have very much information. We have to think through all the possibilities, and we'll say no, this inverse function doesn't exist. Example 5 is an important one. Sometimes we're asked to give information about inverse functions based just on a table of values. So let's take a look at what that might look like. Okay, so here's our table of values, and this is not too untypical. Sometimes you'll see inputs and outputs and actually another function on the same table. So these are definitely our input values, and then we're just going to look at what happens through 2 different functions, f and g, and their output values. And we're going to answer a series of questions and try to understand a little bit more about inverse functions through this table. So here are some questions we want to answer from this table. First of all, find f inverse of -2, find g inverse of 0, find f inverse of 4, and find g inverse of 2. So we'll start right here, finding f inverse of -2. This means that for the original function f, we had an output of -2, and we want to send it back to where it came from. So we look at this table. Let's see. For the original function f, we had an output of -2. So here are the outputs. Do we ever have -2? Yeah, we had an output of -2, and we want to send it back to its original input. So it looks like f of -2 should be 0. F inverse of -2 should be 0. So we definitely want to make a correction here. I made an error in saying that f inverse of -2 was 0 because I took this back here. But if you look at it, this is 1, 2, 3, 4, 1, 2, 3, 4. So -2, actually the inverse of it is 1. So f inverse of -2 is not 0. It should definitely be equals 1. So you'll see it in error in the rest of the video, but this is the correction, and I'm just kind of an amateur video editor, so this is, you'll just have to remember that -2 actually got sent back to 1, even though it'll be in error for the next couple minutes. I just read the wrong line. All right. This is sending the output -2 back to its original input, which is what the inverse function does. Okay, let's think about g inverse of 0. So we're talking about the function g now. We have an output of the function g of 0. Remember, our outputs of g are our inputs of g inverse. So the original function g had an output of 0, and we want to send it back to where it came from. So our original function g had an output of 0 right here, and we want to send it back to where it came from. We just cross right over the f column because that's not pertinent at all to this question. We're just talking about g. So g is going to go back to its input value, and it looks like that should be equal to 2. So g inverse of 0 is equal to 2. Next question, find f inverse of 4. So this is an output value of the original function f, and we want to send it back to where it came from. So here's our function f, and we're looking for an output value of 4. Okay, so we have a little bit of a problem because none of these output values are 4. So we can't take 4 back to where it came from because it was never an output for the function f. So in this case, we would say this does not exist because the function f never had an output value of 4, or DNE. That's just an abbreviation. Okay, last one here, g inverse of 2. So the original function g has an output of 2. We want to send it back to where it came from. So here are our outputs for g, and we're looking for 2. Here it is. So we want to send it back to where it came from. And you probably see the problem with this one. There actually is another output of 2, and it gets sent. It would have to get sent to another place. This is a problem that 2 in the inverse function would have to go to 2 different places. So here we kind of star it. We know that this is a problem. So the problem is in the inverse function, or the inverse relationship of g, 2 would have to get sent to -2 and 0. This is absolutely not allowed with a function, which leads to our the last 2 questions for this example. So is g inverse even a function? And we see that it can't be because it would be forced to send this value 2 to 2 different places, which isn't allowed for a function. So while we're here, we should also ask the question, well, can we tell if f inverse is a function? So can we reverse all of these and keep the rules of a function? Let's see, 3 gets sent to -2, 5 gets sent to -1, 2 gets sent to 0, -2 gets sent to 1, 1 gets sent to 2. Yeah, it looks like there's no problem. We have all unique output values for f, so it's not like we ever come up with some situation like we did here where the same number would have to get sent to 2 different places. All of these are unique, and so based on this table, yeah, f is a function. It follows the one important rule for a function. For our last example of this section, we're going to think about a situation where, say you were standing and you just threw an orange up in the air, and then it came and fell down again. And we want to think of the function of the height of the orange as a function of time. So here is that function that gives height as a function of the number of seconds, -16t squared plus 20t plus 3.5. And so this is going to give the height of the orange t seconds after it is thrown up. And it's thrown up from an initial height of 3.5 feet and an initial velocity, or just meaning a starting velocity, starting speed of 20 feet per second. So I throw it up with some force. And it has that speed initially, but gravity, works on it, and that speed will change, and obviously the height of the orange will change. The first thing we're asked to do is create a table of values for this function. This will give us a good idea of just some data and what's going on with this function. So if I'm going to create a table, I need to think through what are my inputs and outputs. And my input, I know from the formula for the function, is t, which is seconds. And my output is height, which is given in feet. And so I get to pick the inputs, and then the function will tell me what the outputs are. So for this independent variable, I'll pick some like, well, should I pick like -1 for a t? Probably not, because we're not going to talk about negative time. Because our inputs, you know, this is a practical domain, would be positive numbers or 0. And I'm definitely interested in 0 because I want to know what's happening in the very beginning. How long does it take an orange to, you know, be thrown up and then land on the ground? Not very long, probably less than 2 seconds. So we probably want to look at things like, you know, these as inputs. What's happening every half of a second. Okay, those are my inputs, and now I'm going to go ahead and look at the find out what the outputs are from this function. The first one's relatively easy to tell. At 0 seconds, you know, right at the moment that I throw it, if I put 0 in for t, both of these drop out, and so my height is just 3.5. So when t equals 0, my height is 3.5. I kind of already knew that because they told me that the initial height of the orange was 3.5 feet. For the rest of these, I'm just going to have to use a calculator and put those values in for t into the function. When I plugged these input values into the function, these are the output values that I got. So what does this mean? After half a second, the orange is at a height of 9.5 feet. So it got thrown up pretty high. After 1 second, the height is now at a height of 7.5 feet, which means that it started falling down already. And then the formula tells me at 1.5 seconds, the orange is at a height of -2.5. Well, the orange is not burrowing into the earth, so this is actually an impractical output for this situation, as well as 2 seconds. So obviously before 1.5 seconds, the orange has hit the ground. So these are not practical outputs for the scenario, even though they are real numbers that came out of the function. So anytime you have a function, we also have to think about what is the situation of what's going on. Next, we're asked to graph the function, and so we're going to use Desmos, and we'll input this function and make sure our window is the right size and get a picture of what's going on. When I graphed this function on Desmos, this is what I got, and our horizontal axis is time, seconds, so here's 1 second, 2 seconds. Our vertical axis is height in feet, so here's 5 feet and 10 feet. And this picture definitely corroborates what we found in the table. At a time of 0 seconds, which is right here, the function is at 3.5 feet, or the height of the orange is 3.5 feet. At half a second, which is about right here, the height of the orange is 9.5 feet. At 1 second, right here, the height of the orange it's already started falling, and it's at 7.5 feet. And by the time we get to 1.5 seconds, yeah, the orange has hit the ground, and that's why we're getting some negative numbers for these output values. So the height of the orange over time follows this curve, and we're really only interested in, you know, time 0 to time sometime about 1.4 or something. Next, we're asked to find the x-intercepts and the y-intercepts. So x-intercept, and I put a s because maybe there's more than one. The x-intercept is where the function, the graph of the function hits the x-axis. So here's the x-axis. Does this function ever hit this x-axis? Yeah, it does right here. So we're going to find that. And does the graph ever hit the y-intercept? Yeah, it hits, or the y-axis, yeah, it hits the y-axis right here. So this would be the y-intercept, and this over here is going to be the x-intercept. One really nice feature of Desmos is it will find the intercepts for you. If you just click on the point that is the intercept, it'll give you the coordinates. So we find pretty quickly that the y-intercept is 0, 3.5. And this makes sense because the y-intercept happens when x is 0, and we already knew that when x was 0, y was 3.5. This was the trickier one. We weren't sure exactly where this happened, but Desmos gives us the coordinates that when the height is 0, that the time is 1.406. So now a really important question with this function, is there an inverse function? So the real question we have to answer is, are there any output values, so any output values that share an input value? So for example, there are, and for example, at a height of 5, the orange is at a height of 5 2 different times, right here and right here. It's because it's traveling up and then it travels back down through that same height. So if there were an inverse function, we wouldn't know where to send the height 5 back to. Should we send it to this time or to this time? So that's a problem, which means that there is no inverse function here. So no inverse function because there are output values of h that have multiple input values. And just for another example, we don't know what time to assign to h equals 5. When the height is 5, or when it was 6, 7, 8, all of those have multiple input values. So this leads to a graphical test of whether a function has an inverse function or not. It's called the horizontal line test. If any horizontal line hits a function more than one place, then that function cannot have an inverse function. So here are 2 examples of that. First of all, the horizontal line test. If any horizontal line intersects a function in more than one place, that function has no inverse function. So this example here, certainly this horizontal line is going to hit the function multiple places. And so this output value of the function, we wouldn't know which input value to send it back to. So there's no inverse function here. But this function here definitely has an inverse function because any horizontal line only hits it in one place, and it's easy to send an output value back to its input value. This horizontal line test may remind you of another test that you've probably seen before in other classes called the vertical line test. The vertical line test is a test just to tell if something's even a function or not. Can you pass any vertical line? If it hits more than once, then it's not a function. This is definitely a function because every input value has a unique output value. This is not a function because we have multiple input values that get assigned 2 different output values right here and right here. You've probably seen this one before, but horizontal line test is probably something new. So this introduction to inverse functions gave us a lot of great ideas, great topics. What an inverse function does. It reverses what the function does. Notation of f inverse. We needed to know that this wasn't just exponent. And we looked at a lot of examples, graphical, table, formula, word examples of inverse functions. And we talked about the horizontal line test. One last thing also, we don't want to leave this one out, just the idea of existence. Sometimes the inverse doesn't even exist, but sometimes it does. All right, good section.